Hey guys, so here's a quick second one, and then this is it for today. Percent error. Let's say I have someone doing an experiment and they make 38 grams of sodium chloride, right? And their math tells them that they should have made, so this is their experiment, okay? Their math tells them that they should have made 50 grams in theory. So they've done a stoichiometry problem or something. What's the percent yield? 38 grams over 50 grams times 100. This is percent yield, how much you've made. So you go ahead and do 38 divided by 50, and that equals 0.76 times 100, so that equals 76%. Now, quickly, if you want to find percent error, how far off you are, well, you do. If 76% is what you yielded, what's the difference between that and 100%? Oh, I didn't multiply, sorry. So if that's true, then what's the difference between 100? 24. So the percent error is 24%, just by doing it this way. Now, if they ask you how to calculate it, you have to do experimental, okay? Or excuse me, let's do it this way. Okay, so let's do theory. It doesn't really matter, but theory, I'll talk to you about it later. Theory minus experimental over experimental. I'm tired. Over theory, sorry. Okay, so bottom line, it's a difference between what you should have and what you make in lab. A lot of times you'll see absolute value signs, and sometimes you'll see these two numbers are switched, or the two words switch. So you could have this happen. You could have experimental minus theory. It doesn't really matter, does it? Because you have absolute value signs. So it's just a difference. So what's true? What's the difference between 38 and 50? The difference is 12. So I can put this up here. And 12 divided by 50 grams, which is our theory, is going to give you 24%, because you take that 0.24, which is your answer to this, and multiply it by 100. So there's a couple ways you can do this. You find percent yield. Yield means how much you make, right? Your box of brownies says just make a dozen or 2 dozen brownies. That's your yield. If you burn some, it drops on the floor. That's your error. So this is how you do this type of problem. Okay. Significant figures. If I have 4.2, let's do significant figures first, sorry. Okay, 3 kinds of zeros. Zeros in front do not count. There's one significant figure. Zeros in the middle always count. 3 significant figures. 0 at the end only count if there's a decimal. No decimal, 1 significant figure. What kind of zeros here? Zeros at the end, but there's a decimal, so there's 4. What would this be? Lots of zeros. Okay, so these do not count. These do. There's a 0. There's a decimal, so there's 4. How do you need to know how to do this? Well, 4.2 plus 3.64, you're going to add them up. You draw up a line. That line tells you you have to round to. So this is 4, 8, 7. What's the 4 do to the 8? Nothing. So it's 7.8. That's the place that you're limited to. What if you have 2.2 times 3.339? That's your problem. How many significant figures are here? 2. How many are here? 4. This is your smallest value. It limits you. Your answer in your calculator is this. So where do you know to round to? Well, this is 2 significant figures, so you say there's 2 numbers that mean something. Does the 4 do anything? Nope. So the answer is 7.3. What if? What if your answer was 7.3521? What if? The 7 and 3, what would the 5 do to it? It rounded up to 7.4. Okay, it's only what if. So again, there's two significant figures here because there's two numbers here. Here you drop a line and you're limited by your least significant place. Okay? Alrighty. You need to make sure you look at separating mixtures. Distillation. Distillation separates things. To distill something separates things by boiling point. Filtering separates by particle size, right? And chromatography, that's used for things like ink, right? Let's make those, you've done that. Chromatography. I can spell. Okay, when you have ink on your paper and it separates and bleeds, all those different colors are there. Okay, scientific notation. Atomic structure, orbital diagrams. I'm just flipping through just to see if there's anything else I can help you with. Moles. Let me do a stoichiometry problem. Okay. So there you go. Remember, this is a gas. This is gas. This is gas. Okay. Actually, let me do this. Let's do entropy. Okay. Oops, sorry. So thanks for bearing with me, guys. So entropy is disorder. So you look for things from going from very random to ordered or ordered to random. So what's true here? How many moles do you have on this side? 3 moles. What's it doing? It's going to 2 moles. If you have 3 moles and going to 2, isn't that becoming more ordered? Okay. What's some of the states that matter? Well, you have gases here. So gases are all the same. So you look at the moles and it's becoming more ordered. That means entropy is decreasing. The randomness is becoming less. It's more ordered. So entropy is going down. Entropy means randomness. And this is quick, so if you don't get it, you don't get it. All right, so what's true here? Here I have 3 moles going to 2 moles. Again, entropy is going down. When this is a solid, and this is a gas, and this is a solid, what's happening? Here I have my solids, a gas, and a solid. So what's happening? I just have a solid on this side. This is a solid and a gas. This is becoming more orderly, isn't it? And I'm also becoming more orderly here, 3 to 2. So here entropy is decreasing. The randomness is going down. Let's look at this one. Here I have a solid, and it's going to a solid and a gas. Isn't a gas a little crazier? So what's happening? I have 2 moles on this side going to 3 moles on this side. That's getting a little kookier. It's crazier. It's less orderly. I'm going from 2 moles on my reactant side to 3 moles on my products. I have a solid on my reactants, and I'm forming a solid and a gas. Plus, I'm going from 1 item to 2. Isn't it a little more random, a little less ordered? So entropy is increasing. What's entropy mean? Randomness. Again, that's really quick. So let's go ahead and do this. And then I'm going to call it quits. So let's do a stoichiometry problem. Let's say I have 3 grams of hydrogen. And I want to know how many moles of water I'm going to make. Actually, let's do liters. So what am I going to do? 3 grams of hydrogen. I have 2.02 grams of hydrogen in 1 mole. This is hydrogen. For 2 moles of hydrogen, I make 2 moles of water. Right, this is water. And in 1 mole of water, I have 22.4 liters. So when I do my math, I'm going to take 3 divided by 2.02 times 22.4. That would give me 33.27 liters of water. Okay, that's a good stoic problem. Now, what if I had hydrogen, 3 grams of hydrogen, but I also had 5 grams of oxygen, and I wanted to know how much water I can make? This is a limiting reactant. You know that because you have 2 different reactants. So that means you choose stoic problems. So 5 grams of oxygen, 32 grams in a mole for oxygen. And for oxygen in the balanced equation, for every 1 mole of oxygen, I make 2 moles of water. And for every 1 mole of water, I have 22.4 liters. So do your math. 5 divided by 32 times 2 times 22.4 gives you 7 liters. Now, look at this for a second. This is like my noodles and sauce idea. I have plenty of sauce and not as many noodles. How much spaghetti can I make, or lasagna can I make? So look at this. This is saying that if you have hydrogen, you can make 33.27 liters, and if you have oxygen, you can make 7 liters. If you have 5 grams of this and 3 grams of that. Now, can you make 33? It says here you can only make 7. That is if you have enough stuff to react with this hydrogen. If you have enough oxygen, then you can make 33.27 liters. But you don't. You can only make 7, so this is your limiting reactant. That's it. That's your limiting reactant. So that means this is your excess reactant right here, hydrogen. You have too much of it. Don't have enough oxygen. Okay? Maybe you get that. We'll see. So let's go back. I'm going to go ahead and clear my annotations here. I'm going to go ahead and put one more example here. Whoops. Sorry. So let's say I have 3 moles of hydrogen. I don't know how many grams of water I make. So 3 moles of hydrogen. By the way, we're going to do a percent yield out of this so you can see how you apply percent yield to stoic. 3 moles of hydrogen. I know my balanced equation, 2 moles of hydrogen make 2 moles of water. And that 1 mole of water is 18.02 grams of water. So I have 3 times 18.02. That's going to be 54.06 grams in theory. That's what my math tells me. Okay? So Fairley does an experiment and she makes 52 grams. So 52.16 grams is what Fairley makes. Pretty good. Let's see how far off she is. This is what my experimental is. Okay, they give that to you in an equation. They say Fairley made 52.16 grams of water. What's your percent yield? That's what the equation would say. It would say 52.16 grams is what Fairley made in lab. It's bad decimal, sorry. Okay, that's how much she made in lab. Experimentally, what's the percent yield? And this is the information they give you, 3 moles of hydrogen. You need to find theory first. Then you take 52.16 grams, you put on top of 54.06 and multiply by 100, right? And then your equation. So 52.16 divided by 54.06 times 100. Fairly's not too bad. So 96.4. If I was going to do significant figures, I'd only have one significant figure. Okay, but we're not going to do that. They won't do that with this. So 96.4% is her yield. What would error be? The simple way to do error would be to do subtracting from 100. So error would be 3.51. So how would I figure out error? I could do it that way and subtract from 100. That's percent, right? Or I can say, what's the difference? My percent is my accepted, 54.06 minus 52.16 over 54.06 times 100. And if I do that, on the top, you get 1.9 divided by 54.06, and I get times 100, 3.51%. So how about that? Always add acid to water. And I really can't tell you anything more, guys. You need to do your best. I believe in you. Good luck.